Hi, this is Recompile, and in this video we're going to go over some of the more specific details of how ecuflash works when you're tuning your Evo. So in the last video we covered a lot of the basics of ecuflash, how to read your ROM image, how to save it, what a map consists of, the various scalings that live within a map definition, and we covered the basics of inheritance in ecuflash, in which your parent ROM XML definition gives you the basic structure of your ROM image, and then in your specific ROM ID's XML file we get the specific addresses of where all these tables are defined within your specific ROM version. So what I'm going to do is I'm going to browse out to my installation folder for ecuflash. Yours will probably live in C/program files, openecu /ecuflash. In here we'll have, in particular, the folder we're looking for is the ROM metadata folder. The ROM metadata folder basically contains the XML files that we were visually editing in the last video. We'll just jump right into Mitsubishi and Evo. So here we have a nice long list of all the possible ROM IDs that ecuflash is aware of. It's possible that your ROM version is actually not listed here. If that's the case, you may have some trouble editing your ROM image in ecuflash. You may have to try to find the definition file from someone else in order to be able to gain access to what's in your ROM. But hopefully yours is listed here and we can jump right in and take a look. It also includes all the parent base XML files, Evo 9 base, Evo 7 base, which actually also applies to the Evo 8 ECUs, and so on. So let's first take a look at Evo 9 base 2008-1101. This is one of the parents that was listed in our last video. We'll just open up with Notepad for now. So the XML file here defines the XML ID, basically the name of the file, and then a whole bunch of scalings. These are all the possible scalings that ecuflash will know about when dealing with an Evo 9 ROM. It contains all the formulas to do all of the conversions to make all of the binary data in the ROM image readable to you as a user. Scalings are typically defined at the top of the ROM image just for readability's sake. Below that we have the table definitions. So again, this is the same type of data that was listed visually, just now listed in XML. And whenever someone adds functionality or revises functionality, you're probably going to be pasting new information into an XML file. The information will consist of table definitions, describing the name of the table, what category it belongs in, basically what group to put it in when you're looking at an ecuflash, a 3D table or a 2D table, and other possible settings. So including the scaling to use, and so on. Now you'll note that basically the same as we had in our last video, there is no address definition in this XML file. So this XML file is just setting us up for what a table looks like, but not necessarily where a table lives. That will be defined in the specific ROM ID version XML file, which we'll look at next. So if we go down to the bottom of this XML definition file, or almost to the bottom, you'll see that I've actually added some additional features. In particular, what I've added is some OBD2 inspection patches. This is a great patch. I think Akamas and Mr. Fred have worked on this, but basically it'll force all of the OBD2 inspection checks to return passed. So just so you can understand how this is accomplished, what they've done is they've gone out and they've found what the OBD2 inspection tables consist of and also where they live. And what we've put in this Evo 9 base XML file, something that all Evo 9 ROMs will have in common, is just the layout of these tables. So we have some 1D tables that just consist of a single value. We have some 2D tables that will consist of just a couple values, and we have some descriptive blobbit tables, which basically a blobbit is essentially a way to access individual bits within a specific byte in the ROM image file. All that means is the ROM may handle several different features in the same byte, and in order to be able to turn one feature on and not affect the other, or one feature off and not affect the other, we do that with blobbits by allowing us to edit a single bit at a time. So this 1 byte of data contains 1, 2, 3, 4, 5, 6, 7, 8. It contains 8 different bits to make up the byte that exists for this particular check. It consists of the EGR, the O2 sensor, and so on. So using a blobbit scaling, we can get really specific and say, well, we want the heated catalyst check to return pass, but we don't care about the evap system, and so on. This is a more recent development in ecuflash, and if you have an older version of ecuflash, you may not have blobbit support, but you definitely should update, because it's great to be able to go in and see what each bit represents in the ROM. I also have a heater patch, which basically just sets us up with a bunch of addresses. We have some other ECU periphery data. So all this stuff that I've added to the end, all you really need to worry about is that this is where you would add content if you're adding new table definitions into an XML file. So if someone says, oh, you don't have your MUT table represented on your ecuflash, or if someone says just go into your MUT table and change, MUT00 to this and so, well, you may not have a MUT table visible in your ecuflash, and if it's not visible in ecuflash, it's because it's not defined in these XML files. So what you'd have to do is find what exactly belongs here and paste it in. Once it's pasted in, you should have access to it in ecuflash visually. You just make sure that you get everything in before the end ROM tag. So that's what our Evo 9 base looks like. We basically don't have any addresses, we just have structure. If we look at our 885.90015 XML, what we get here is, you'll notice it doesn't have any scalings, or has one scaling at the top specific to this XML file, but it doesn't have any other repeated scalings. There's no need to repeat information that's already included in the Evo 9 base XML. All we really need to specify here is what the table name is and what its address is. We don't necessarily need to specify any other structure, and in the case of a high-octane fuel map, for example, all we need to tell it is what the name of this table is, or this X or Y axis is, and where to look for it. The other thing that's interesting to note here is that some maps share the same axis locations. So our high-octane fuel map and our low-octane fuel map, if we look at the address for engine load, on the high-octane fuel map, it's at 6EC8. In our low-octane fuel map, it's also at 6EC8. This is important to understand because if you change the engine load scale on one of these two maps, it will affect the other one. So you have to be conscientious of what shares those same addresses. In most cases, the fuel maps will share their load and RPM scales. The timing maps will share their load and RPM scales, and so on. So it should be pretty logical of how it's set up, but just something to be aware of, that when you change one, you're also going to change the other because they live at the same place. They live in the same address in the ROM. So just like we did in our Evo 9 base XML, if we scroll down to the bottom, you'll see that I've added some other stuff for OBD2 inspection tables. You'll notice that it's a lot smaller of a section here because I don't need to restate how these tables look. All I really need to do is say this table lives at this address, and that's the end of it. This makes writing XML files from scratch really easy for developers or people who are working on patches. They can write the table definition in a base file once, and then just define the addresses for a whole set of specific ROM IDs with minimal work. Again, if you need to add information, you're going to be adding it towards the end of this definition file before the end ROM tag. So I just wanted to show you how these tables are set up in XML, so that in the event that you need to add some features to your ecuflash, you'll be doing it through these XML files. Let's take a look at ecuflash itself. So before we looked at our high octane fuel map, we made a few random changes. Now, keep in mind that nothing gets saved unless you save it, so feel free to cancel, close out, and go back in, which I'll do right now just so we can start from a clean slate. We'll close the ROM out. Give me a nice warning, we'll say no. Go back in. So as we stated, the high octane fuel map gives you your target air-fuel ratio. Now, it's not an exact target air-fuel ratio, but it represents something somewhat in that range in most cases. If you have a highly modded Evo or something that's not even close to stock, your values may be all over the place, and depending on things like your MAF scale, your intake, your injectors, and how well the rest of the tune is combined, the values in this fuel map are very arbitrary. So one car will use one will like one particular type of value, and another car may use something completely different. So don't feel that this fuel map is specific in any way or is universal in any way to multiple different Evos. You don't really want to copy anyone else's fuel map, specifically because you have no idea if their setup is anywhere close to yours. So just to give you a general overview of what lives in the ecuflash as far as what tables you have access to. The fuel map and the timing map are probably the most commonly edited maps. If you're familiar with tuning already, you probably specifically have been looking just for these guys right here, first and foremost, because ignition timing and fuel are probably the two key components to tuning a car. If you're not familiar with tuning at all, we'll get into tuning practices in another video. Some other things you'll have access to here are specific rev limits and speed limits. In this case, we've got our stationary rev limiter from the factory is set to 5,000 RPM, and our engine rev limiter 7606. Now, you may wonder, why is it 7606? Well, this is a good, important thing to bring up. If we try to set this guy to 7600, you'll see it doesn't go to 7600 exactly. It goes to 7599. And the reason that is because if you remember, this 7599 is not what's stored in the ROM. It stores another number, which is converted to 7599 for your viewability here. So if you're trying to change a value in any ecuflash map and it won't get to exactly the value you're trying to get to, it's probably because it needs to round off, because this is not a precise number, it's a converted number. So we'll just set that back to 7606. Now, one thing I want to state just kind of off the bat is that the knock sensitivity maps and so on, while they may have some use for advanced tuners, people with built engines that need to specifically retune the knock sensor to eliminate phantom knock, you don't really want to touch these if you're a novice tuner or if you have a stock or mostly stock Evo. Mitsubishi has set up the knock sensor very well from the factory. It's very efficient, and if you have a problem with knock, the last thing you want to do is come into these maps and start messing with the knock sensor thresholds. The first thing you want to do is try to fix your tune. Try to get it to stop knocking. Now, if you remember, when we bumped out into that XML directly, we looked at something called blobits, and those can be represented here. Actually, why don't we look at the OBD2 maps, because that's what we looked at in the XML. So look at the OBD2 inspection maps. This is an example of a blobits map. So it's our 8 bits that make up the 1 byte. Now, if you do try to edit something in these values, you may notice that there's a problem. If you hit equals and type in 1, the value doesn't hold. I can try it again, it just does not hold. So that's just kind of a deficiency with ecuflash. When you're editing a blobits table, you have to use the increment or decrement keys on the keyboard. So the right bracket and the left bracket. Maybe that'll be fixed or changed in a future version, but for now, if you're trying to change a blobits table, if you're trying to change a single bit, just do it with the increment or decrement and not with the equals. Before, again, we get into any specific type of tuning practices, I want to educate you or let you know of what the MUT table is. So Mitsubishi has created their own protocol for data logging and for diagnostics, system diagnostics. It's called the MUT protocol, and you're probably familiar with a program called EvoScan that can take advantage of this protocol for data logging purposes. So if we bump out to EvoScan real quick, so EvoScan lists a bunch of different things that we can data log, and it lists them along with a request or a request ID or a request address. This actually corresponds directly with your MUT table in your ECU. Now again, if you don't have a MUT table listed in ecuflash, you're going to have to add it to the XML before you can see it. And I recommend it's one of the first things you do when you're trying to tune your Evo, because having access to this MUT table is key in setting up the ROM before you do any tuning at all. You're going to want to make some changes to the MUT table in order to make data logging more beneficial to you and make it much easier to tune. So what you want to do is get your MUT table listed. You can find the official 2-byte thread in the ecuflash forum on Evolution M. The official 2-byte thread should list your ROM ID and whatever XML that's needed to paste into your ROM ID's XML file. And once you paste that XML in there, close out ecuflash and reopen it, you should have a MUT table listed here, which you can then click on and expand into this giant 3D MUT table, which is essentially a list of addresses. Now obviously this doesn't make any sense to anyone just looking initially. We can't really tell what any of this means, so allow me to explain. So in ecuflash, when I said that the request ID here corresponds with a MUT table address, what that means is when we want to log RPM in EvoScan, what we're going to do is we're going to log MUT21. MUT21 is associated by, as you can see, the y-axis here explains that this is MUT2X, so everything on this row is MUT2. This first one here will be MUT20, 21, 22, and so on. So if we need to look at RPM at request 21, we're going to look at MUT21, 6B29. What this represents, now this is very important if you understand, if you're going to understand how EvoScan works, you understand how the MUT table works, and if you're going to understand what it is that you're doing when you come in here and change these values. This value, 6B29, is an address in your ROM that will return the current RPM of the engine. So all EvoScan is doing is saying, whatever is in MUT21, I'm going to assume that that's RPM. If we go in here and we change MUT21, it won't be logging RPM anymore. It'll be logging some other value that some other memory address in the ROM. So 6B29 is what the stock image off the ECU is set to, which is fine. We have no need to change that. What you might change in the MUT table specifically is 2-byte load, possibly 2-byte airflow, and possibly some other features if you're having trouble with one aspect of your tune and you need to start logging something, say MyVec intake cam advanced position, if you need to log some other attribute of the ECU that it's just not set up to log by default, you're going to define it in the MUT table. So understand, when you're changing these values, all you're doing is changing what it is that you can log with a data logger. You're changing what addresses the logging program will be able to gain access to. Now, when I say 2-byte load, you may not know what that means. You may have heard it, you may know exactly what it means, but I'll assume that you don't know what it means. If you remember on our high-octane fuel map, we had load along the x-axis. And again, this was also on the timing map, and it's on several other types of maps as well. It's a very important concept in tuning, especially with turbocharged, supercharged cars, because engine load represents airflow, it represents boost pressure or vacuum. So if you want to be able to fully tune your car while it's under boost, which I will assume you do, you're going to need to understand load, and you're going to need to understand 2-byte load, specifically as it relates to the Evo. So by default, from the factory, there is no value in the MUT table that will efficiently allow us to data log what the engine load is at any given time. So we run into the problem of the car knows how much load the engine is under, but if you were data logging it with EvoScan, there is no address in this MUT table from the factory that represents that load accurately. So there is no possible configuration in EvoScan that will allow us to log load accurately. The only way we can do that is by coming into the MUT table, making changes to allow us to gain access to these other addresses in memory to log them with EvoScan. And the reason we call it 2-byte load is because it's obtained by logging 2 separate bytes and combining them to form the one load value. Now, the reason we do that is because in decimal form, 1 byte represents the values from 0 to 255. And because the ECU is granular enough to see load in very small increments, even increments less than 1, it doesn't really do us any good to only have 255 values. You can tell even from the factory our load scale goes beyond 255. It goes to 260, 280, 300. And if you have a high horsepower car, you're probably seeing loads higher than 300. So 1 byte, while it represents values 0 to 255, doesn't efficiently represent all the possible load values that the ECU could be experiencing. Now, there is an exception to that, which I'll get to in just a moment. But for now, assume that 1 byte is just not enough to log load. So it was determined that by changing 2 MUT table addresses, we can actually log 2 separate bytes and interpolate from them what the true load value is. We can actually log the values from 0 to 255 twice, and the first value will give us any number from 0 to 255, and the second value will give us a multiple, giving us a very, very high maximum possible loggable load with 2-byte load. So now we've basically removed the cap. 255 is no longer a cap. We can now log several, we can actually log 255 times that amount, which is great. So in EvoScan, you're going to see a request ID, but you'll actually be able to go in and edit the EvoScan XML to see what the second byte is in 2-byte load. So let's take a look at the evoscan XML. That's stored under the program files evoscan, whatever version evoscan you use, data settings, and data XML. Again, if you're tuning evos, you're going to really have to love these XML files. You'll probably be seeing them a lot. So this defines all the different aspects of evoscan. We look down to our mode 2 data list items. What we'll find is I've defined a row here for 2-byte load, and I'm going to log request ID 00 and request ID 01. That corresponds to MUT00 and MUT01 in the MUT table on my ROM. Now, as it is from the factory, MUT00 and MUT01 are not the correct values for me to log load, or log 2-byte load. So as I said, what you're going to need to do after you've got your MUT table defined is you're going to have to change these, and you'll change them depending on what people have discovered the proper address is for 2-byte load in your ROM. And again, you'll change these by hitting the equals sign. Now, you'll notice that there's a description here that you can enter hex values by starting with 0x. So try to remember, if you're not entering in a decimal value, if you're entering in instead a hexadecimal value, always prefix it with 0x. So if I was to change this to 6A22, for example, I would type 0x 6A22. And you'll see that value will change. So now when I log MUT00 with evoscan, I'm going to be logging a different area in memory, and it'll return a different value. So if you're having problems with evoscan logging data that just doesn't seem right, either your request ID in evoscan is pointing to the wrong MUT table address, or the MUT table address is pointing to the wrong ECU memory address. One or the other. In most cases, you'll find that the MUT table hasn't been updated to point to the appropriate memory address. So again, just to give you another, just to reiterate here on what the MUT table represents. The MUT table represents all the possible values that you can log using a data logger program. It does that by pointing to memory locations in the ECU while it's running, and those memory locations will change depending on what it is that you need to log. From the factory, certain things just work out of the box. Certain things like RPM, throttle position, timing, those are straightforward and they're already set up in the MUT table, so there's no changes you need to make in order to log them. But in order to log things like 2-byte load, 2-byte airflow, and so on, we need to edit these addresses in the MUT table in order to enable logging of those features. So that's an important thing to learn before you start tuning at all, is learning how to edit the MUT table, learning what your specific addresses are for the MUT table itself, and then for things like 2-byte load and 2-byte airflow. Those are important to set up because you don't want to have an estimated or calculated load or an airflow that's clipped at a certain value that you can't read beyond. So to get the most accurate information possible while you're data logging your car, you want to make sure that the MUT table is accurate. So one last thing that we'll cover in this video is just taking a look at some of the other maps besides a fuel map and a timing map, just so you can understand what it is that you're looking at and what it is that you'll probably be tuning down the road. So as I said, the high octane fuel map, high octane ignition maps are predominantly what gets tuned or what gets adjusted. Now, to understand what the low octane map represents, all you have to realize is that the NOx sensor, as we discussed earlier, will utilize this other map, this other low octane fuel map, if there's a significant amount of NOx that the NOx sensor detects. So if we look at these two side by side, or top to bottom, you can see that the high octane fuel map on the top here and our low octane fuel map on the bottom. So all this means is that when we experience a significant amount of knock, we'll be flipping from one map to another, or we'll be interpolating between the two. So basically it'll take values from here and values from here, and depending on the amount of knock that you're experiencing, it will determine how much fuel to mix. So if you're trying to tune fuel, if you're trying to tune timing, and things that you're logging just don't seem to match up with what you see in the maps here, and you're experiencing a significant amount of knock, it's possible that you're interpolating between the high octane and the low octane maps. So ideally, you don't want to have any knock, so you won't be interpolating between these two. And the other best practice, not to go into too much detail, but is to set these low octane maps, which there are also some for the ignition, significantly more conservative than the high octane counterparts. Because what you don't want is a low octane map that gets resourced while you're under heavy knock to be just as or even more aggressive than your high octane map. You basically want it to fall back on something that will keep the engine safe, keep the car safe. So some of the other things that we expose here, things like injector pulse width adder. So if you're cold cranking the car, how much fuel it's going to put in there. Just to give you a quick example of where something like this might be used, if you put a significantly larger size injector in your car, you're going to notice that it just does not want to start. And that's because these cranking IPW adder values are assuming that you have a stock size injector. So if you have, even if the engine's nice and warm, it's going to be adding a 3 millisecond injector pulse width, which may just be too much, and you might be flooding the engine trying to start it up. So you'll have to pump the gas pedal, get the throttle body open, get some more air in there, and get it to fire off. I noticed this when going up to 1050cc injectors. So what you do in that case is basically you come into this injector pulse width table. You could even bulk select the entire region and go into edit, multiply data, and in my case where I've basically doubled the size of my stock injectors, I can multiply these guys by 0.5, 1/2, and that'll give us a more reasonable injector pulse width adder for while we're cranking the engine. So basically making a simple change like that turned my car that just did not want to start into a car that starts just like stock. So that's an example of what you'd use for the cranking IPW adder table. Now again, not all ROM versions have this ROM, and you'll note that as cars got progressively older, as we got to the 04, 05, 06 Evos, Mitsubishi seemed to add some features that the older ones just didn't have. So it does kind of stink if you're on an 03 Evo and you just don't have some of these tables. I've tuned some 03 Evos that this table doesn't exist, or the airflow offset table doesn't exist. If you can't find it, that could be why. If you're on an 03, 04, if you're on an older Evo, or if you don't have an Evo 6, or I'm sorry, if you don't have an Evo 9, obviously you won't have a MIVEC cam intake map. Some of the other things you'll notice, immobilizer. This is a pretty important but very basic 1D table. It's just whatever value that your immobilizer in your car is programmed to. So if you need to take your ROM and give it to someone else to tune, or if you need to edit someone else's ROM, you want to be aware that the immobilizer is associated with their car, and that if this value changes, the car won't start. Now there are ways to disable the immobilizer, which we may get into in a different video, but be aware that this value is key to getting the car to start. And if that changes, or if you use a ROM from someone else and you try to send it, flash it into your car and start it, and the car just doesn't start, it's probably because the immobilizer isn't set up correctly. Lean spool, just to get into the real basics of it, is the additional leaning of the air fuel mix by the ECU when it believes you're spooling up the turbo. So there's a lot of different tables here. I mean, you'll find that a lot of the different tables that have been defined in ecuflash, they may seem overwhelming to look at, but in all honesty, you won't be using a lot of these. And in many cases, people actually just disable lean spool altogether, and the reason is because it can make tuning air-fuel ratio very annoying, because what's happening is it's taking the values that we've defined in our fuel maps, and it's applying additional leaning or additional reducing of fuel to try to assist with the spooling of the turbo. So we've found, or most people have found, that disabling lean spool completely kind of makes a more consistent tuning approach when tuning air-fuel ratios. Now, if you remember, here's probably a good time to look at it. If we adjust the scaling values in one of these timing maps, let's say we set this guy to 8,000. And then we take a look at one of our low octane timing maps. You notice that the 8,000 carried over to there as well. So that's just kind of to point out the fact that these guys are looking at the same address, and if we looked at their table definitions in the XML, we'd see that they actually, these scalings live at the same address. You also note that if we compare a high octane and a low octane timing map, that the low octane is running significantly less timing than the high octane. And that's intentional, because as I said, if the car is experiencing significant knock, what we don't want is to increase ignition timing, because too much timing is possibly what caused the knock to begin with, or it could be poor fuel, etc., or overboosting. I won't get into too much detail about what the other tables are in here, but you can control quite a bit. I mean, obviously that's pretty apparent. When you open up ecuflash, you get a whole heck of a lot of tables, most of which probably won't make much sense to you until you have to go to use them for the first time. But you can control the stock boost control solenoid. You can control how much air that boost control solenoid is going to bleed away from the wastegate. You can control all the idle stepper control valve, target idle. You control the rev limits. You can control other ECU periphery options. ECU periphery is basically, a feature of the ECU. Particularly, maybe it controls a solenoid. Maybe it controls the logic to perform a specific check that would throw a check engine light. There's one to control the immobilizers, one to control the EGRs. There's an ECU periphery for a lot of the functions of the ECU that can be disabled in these ECU periphery tables. So if you're looking to disable something, if you're looking to turn off a particular check engine light because you know it's not anything real or anything that's really a problem, it's going to be done through the ECU periphery tables, the Blobitz tables we've defined. You here see just I've populated some of these guys with the codes that are associated with that. So if I happen to be getting, let's say I'm getting this evap incorrect purge flow P0441 check engine light code. If there is something wrong with that particular code getting thrown all the time, and I know it's not actually an issue, I just come in here and remember we have to use the decrement increment options. I can turn off that ECU periphery, and that code will never get thrown anymore. So it's kind of nice. If you happen to, if you have removed the stock boost control solenoid and you use a manual boost controller, and the stock solenoid isn't even in the car anymore, it's completely gone, disconnected, you'll want to come in here and turn off the ECU periphery. You don't get a check engine light. So that's some more intermediate explanation of ecuflash. We've gone over a lot of the XML files, raw editing of the XML. We've gone over some of the tuning concepts and some of the table uses that we have set up here. And in future videos we'll get into more specific tuning styles and how to actually go about making changes to these guys, more than just the MUT table changes that we've done so far in order to enable advanced logging.